All right, so we're going to take a look at factoring special cases. There's really nothing unique about special cases other than the outcome of the answer or the factorization. So first, what we want to do is, as always, keep our checklist here of our factoring rules. Always look for a greatest common factor. Okay, so the first thing we look at is it's a 1, 6, and a 9, and we do not have greatest common factor. Second, we look to see if a is equal to 1. And if a is equal to 1, then what we have is typical diamond problem. So set up your diamond. You take 1 times the positive 9 and you put it in the top of your diamond, and your middle term goes in the bottom of the diamond. Everything here is positive, so we don't have to worry about negative signs. All right, now what we're going to do is fill in our diamond and complete it. And we're looking for factors of 9 that could add to 6. So 3 and 3, they multiply to 9, but they add to 6. So our factors are going to be x plus 3 and x plus 3. So the uniqueness, the special case, is that we have the same quantity times itself. So the way we would write this for a final answer would be the quantity of x plus 3 and squared on the outside of it. And that's what makes this a special case. Okay, because this would be our final answer. Again, to check it, remember a quantity squared means a quantity times itself. X squared plus 3x gives us 6x, and 3 multiplied gives us 9. So you could go back and check. All right, let's look at another one. Okay. This is another case that would be considered a special case. Okay. Again, we look for a GCF, 1, 10, and 25. We do not have a GCF, so we go right for our diamond. And 1 is our coefficient of x squared. So 1 times 25 is 25, and it's positive. But the middle term is negative, so it's negative 10. So we're looking for factors of 25 that could add to a negative 10. Well, what comes to mind to give you a 10 is a 5 and a 5. But now we need a placement of signs because we need it to add to a negative 10. So to multiply positive, they'd both have to be negative. And to add to the negative 10, they'd both have to be negative. So you double check it, it works, and you write your factors. So x minus 5 times the quantity of x minus 5. And what's unique is you have the same thing times itself, the same quantity times itself. So it's x minus 5, the quantity of x minus 5 squared, and the square is on the outside. And this is our final answer. Okay, and then you can check, as always, x squared, negative 5x, minus 5x, negative 10x, negative 5 times negative 5, positive 25. Okay, so that's the uniqueness that makes this a special case. All right, next. What you notice is we are missing the x term, or what we call the middle term. It's not there. So what we can do is we can put in a 0 into that term so that we have it there and make it a trinomial. So we have x squared. Now we're going to add the 0x. We're going to give it the middle term that's missing, and minus 4. Okay. All right, so GCF, 1, 0, and 4, no GCF. So now what we're going to look to do is a diamond. We see that the A value is 1, so we do our diamond. And we do 1 times negative 4, which gives us a negative 4 in the numerator, in the top of our diamond, sorry. And a 0 goes in the bottom. Factors of 4 that could add to 0. Well, 1 and 4 won't work because it's going to give us 5 or 3. But 2 and 2 would work if one of them is negative. So 2 times negative 2 is negative 4, but 2 plus a negative 2 is 0. So our factors are x plus 2 and x minus 2. And that's our final answer. Now to check it, x squared, positive 2x minus 2x is 0x, so it won't be there. And positive 2 times negative 2 is negative 4, and you're good. So this is what makes it unique, is the fact that we're missing a middle term here. Now, I don't know if you guys, if you paid attention way back when we were talking about multiplying these types of polynomials or these binomials, but when we got to an answer, we said that these were missing the middle term when we put it back. So if we look at this, x times x gives us x squared, and 2 times 2 gives us 4, but 1 has to be negative to give us a minus 4. This is called the difference of squares. So some folks are really, really good at remembering this, and they would be able to say, hey, that's a difference of squares. So instead of putting in the 0 middle term, you might be able to say, I recognize a difference, meaning subtraction, of squares, which means I have an x and an x. I have a 2 times a 2, but one's negative. So therefore I can say x plus 2, taking one of each, and x minus 2, taking one of each here. So it depends on you if you will recognize this as a difference of squares. Okay. Or if you don't, it is not the end of the world. You put the 0 term in for the middle, and you factor like you always have. All right, so those are the two ways that you can do this. Put in a middle term or recognize a difference of squares. Difference meaning subtraction. Let's try another one. X squared minus 9. Since we're on this, we can see it's a difference of squares. We just learned about it. So x times x, 3 times 3, one of them's minus or negative. So x minus 3, x plus 3. Or we don't recognize it, which is perfectly fine. We put the 0 in for the middle term because it's missing, and we always add it. No sense in playing with signs. Build your diamond. 1 times negative 9 goes in the top of your diamond, 0 in the bottom. Factors of 9 that could add to 0 are 3 and 3, one of them being negative. Double check it. And then it's x plus 3 and x minus 3. And again, it doesn't matter what order you put the quantities in, which one comes first, but it does matter what's inside them. So either way, you're going to get the same result. Let's check another one, a little trickier one, a little higher numbers. Ooh. We have 36x squared minus 49. Okay. And we're missing the middle term. So this is a really good case of when the difference of squares comes in very handy, because 6x and 6x give us 36x. And 7 and 7 give us 49. One of them has to be negative, though, for the minus 49. So our factors would be 6x plus 7 and 6x minus 7, or 6x minus 7, 6x plus 7. We obviously didn't have a GCF. You always check that first. All right, so this is a definite, like, hey, this is a difference of squares. I can do this quickly because I recognize it, and I can go from there. If you do not recognize it, even though the numbers are large, you're going to put in a 0 for the middle term. And then you're going to have to get out a calculator, okay, because the numbers are going to be quite large. And this is what I always say about when this happens. 36 times a negative 49 is going to give you negative 1,764. 0 goes in the bottom. Now, I would take the square root of 1764. So the square root of 1764, would get your calculator out and hit your square root button. You'll hit the second function key above the x squared, and you'll get your square root. Okay, so it would look like that. So you'll hit second and x squared and put in 764. And if that's a perfect square, it will come out as a perfect square, which is in this case 49, or 42, sorry, 42. Okay, so that means 42 will go here, 42 will go here. One of them is negative. And so what you're going to have is 36x plus 42, because now you're doing this the other way, where a is greater than 1. And you'll have 36 plus 42, x plus 42, minus 42, getting ahead of myself here. All right, so I'm going to rewrite that. 36x plus 42 and 36x minus 42. We'll just ignore that one. But now you have to reduce each one of these because we didn't have a GCF, but we can't leave these like that. So each of these can be reduced by 6. So 6 divides into 36 6 times, leaving us with 6x. 6 divides into 42, 7. And the same thing here. So we'll get 6x and we'll get minus 7. So either way, you're going to wind up with the same answers, whether you recognize the difference of squares or you go about it looking for see if a is equal to 1 or greater than 1 and do your diamond. All right, next. 3x squared minus 48. Okay, again, look for a GCF. We can factor out a 3. So 3 divides into 3 once, giving us x squared, into 48 16 times, giving us minus 16. Again, this is a difference of squares inside your parentheses. So if you recognize it, okay, because of the minus, and x squared is x, and 16 is 4 and 4, even though there are other factors, because we're missing a middle term, look for difference of squares. So keep your GCF, and then it's x plus 4 and x minus 4. Okay, because one of these has to be minus for the negative on the 16. If you don't recognize this, you keep your GCF of 3. Build your diamond. Okay, you're going to say 3 times x squared plus 0x minus 16. Put negative 16 in the top, 0 in bottom, 4 and negative 4. And you're going to get 3x plus 4 and x minus 4. So either way, you will come up with the same answer, depending on what you recognize. All right, this is my all-time favorite factoring problem because a lot of kids mess this up. It's a difference. It's of an x squared, which is x times x, and a 1, which is also a perfect square. But one has to be negative. So it's x minus 1, x plus 1, or x plus 1, x minus 1. Or, if you don't recognize it, put the plus 0 in, build your diamond. 1 times negative 1 is the top, 0 on the bottom. Factors of 1 are 1 and 1. One of them has to be minus so that you can, or negative to add up to 0 and multiply to a negative 1. And you get x plus 1 and x minus 1. So again, depends on what you recognize and what you don't. You have alternatives. And last but not least, x squared plus 81. We become robots. We say x squared is x and x. All right, 81 is 9 and 9. And then you go to place that minus sign and you realize there is no minus sign. This is not a difference of squares. Difference of squares means they have to be subtracted. This is being added, so none of this will work. So the answer stays as it is, which is x squared plus 81. Or sometimes you will be asked to write it as prime, which means it's not factorable. Or you might be asked to say, is it or isn't it factorable? So you can just write not factorable. And that would be it. Either one of these 3 answers would be acceptable. And that is how you factor special cases.